Okay, so we're going to talk about now applications with natural logs. So we're going to look at measuring the age of rocks, and so we're going to look at to find the age of rocks is T is this equation is 1.26 times 10 to the ninth. We're going to multiply that by the quotient of ln, which is the natural log, right? The natural log of 1 plus 8.33 times a over k, and then that is divided by ln of 2. Okay, so this is the formula for the age of a specimen in years. So the age of a specimen in years. And so we're going to go ahead and find out where A and K are the numbers of atoms of argon 40 and potassium 40. So A represents argon 40 and K represents potassium 40. And this is a formula that geologists use to measure the age of rocks. And so first we want to find out how old is a rock if A equals 0 and K is greater than 0. So, right, K needs to be greater than 0 because if K is in the denominator here in our formula, that means we couldn't do that, right? So we're going to go ahead and figure out what this is. So if A equals 0 and K is bigger than 0, that means K could be, you know, like 0.00001. That's fine, right? It's bigger than 0. But if my numerator on top is 0, that means our A over K would equal 0, right? So we can go and plug that 0 into this formula. So we're going to use this here formula. We're going to plug in 0 in for A over K. So we have 0 times 8.33, which is going to be 0, right? And so since that is 0, we're going to add 1 to that, so that is 1. So really we're going to take the ln of 1, divide that by the ln of 2, and then we're going to multiply it by this coefficient out here, which is 1.26 times 10 to the ninth, and that's going to tell us our age of this specimen here. So this is going to be ln of 1, because this is 0, and 1 plus 0 is 1. So we're going to take ln of 1 over 2. And remember, ln of 1, we haven't talked about this before. We know ln of e equals 1, but what does ln of 1 equals? Well, remember from the last video, ln is the natural log, right? So log with base e, so log of base e of 1. This is asking e raised to what is 1? Well, this answer to all these questions, right? The answer to all log base a of 1 is always 0, right? So this is 0. Oops. I'm just kind of filling in our formula here for t. So t equals, all right. So this up top is now going to be 0, and what's 0 divided by ln of 2? Well, that's just 0, right? And then 0 times this constant out front is 0. Okay, so this rock is new because it's 0 years old, right? Like a baby. Just because a baby is 0 years old doesn't mean you don't have a baby, right? So it's just not. It's just new. Okay, so this rock, because t equals 0, it's just a new rock. So it's a new rock. Okay, the second part of this question is if a sample of a granite from New Hampshire has the ratio, so the ratio of our argon 40 and potassium 40 is the ratio A over K of this piece of granite, or the sample, is 0.212, how old is this sample? So then we can go ahead and just use that ratio. So that's our AK, remember, and A over K. And then we're going to times that by 8.33, and then we're going to add 1 to that. Then we're going to take the ln of that. Then we're going to divide that by ln of 2, and then we're going to times that answer by 1.26 times 10 to the 9th, and that will give us our age in t, right? So I'm going to take on my calculator, I'm going to type point 212 and times that by 8.33. Okay, and that's 1.76 6596, and now I'm going to add 1 to that. So I don't erase anything from my calculator. I'm continually typing this in, right? So I have this number now, it's 2 something. Now I'm going to type in my calculator. I'm going to hit the ln button, and then I'm going to hit my answer button that holds this answer in there. I'm going to close that parenthesis. Okay, and then I want to hit divided by, and then I want to hit ln. Then I want to put in my number of 2. So then I'm going to close off that parenthesis. And then now I'm going to hit enter. And then I'm just going to hit multiply by. So this answer is 1.46. So this answer right here is 1.47 if I round it. Okay, and I want to hit multiply by 1.26. So when I hit this multiply, I want to put what I'm multiplying right here in parentheses. Parenthesis 1.26, and then times 10, and I want to hit my raise 2 button, and that is 9, and then I'm going to close off that parenthesis like that, and then I want to hit equals, and I get a huge number that says this piece of granite is 184903169. So it is 1, 2, 3. Let me make sure 18494. There's another 4 there. So this is actually 1 billion years old. Alright, so it's about 1.8 billion years old. Alright, so then you can do these problems. In reference to this is number 77. Then we'll go ahead and do another example of the global temperature increase. Okay, so we're going to check out the modeling of global temperature and the increase on it. And we have this idea of radiative forcing. And that is the idea behind the solar radiation being trapped by carbon dioxide. And we have this formula that finds this radiative forcing as R. And the formula is equal to K times ln of C over C sub 0. Now, C sub 0 is the pre-industrial amount of carbon dioxide, and where C is the current carbon dioxide level, and then K is our constant. And so we want to figure this out. So they're going to have to give us a few things in order to figure this out. So they're going to give us C is equal to 2 times our pre-industrial amount of carbon dioxide. So our current amount of carbon dioxide is 2 times that of our kind of our initial amount, our pre-industrial amount of carbon dioxide. Okay, and so we can then and then also it kind of gives us our constant, our K is between 10 and 16. Okay, so that means that our C over CO would be 2CO, C sub 0, over C sub 0. Right, so these are going to cancel out, so I'd get 2 here. So I get K times ln of 2, right? It's K times equals R. All right, now we just need to know what our constant is. So looking at the problem, it says that it just wants to know, is this equation right here, is this a linear representation, or is this a logarithmic representation between r and k? So linear is kind of like a direct variation equation, right? Y equals kx, right? So to be a logarithm, you would need your variable, right? You would need a variable in with your log, right? So y equals log of x, right? But here, this one, L2 is just a number, right? So it's just a constant. So this is actually a linear relationship. So that would say, I mean, ln of 2, we can go ahead and actually figure out what that is. But it's going to be a decimal that goes on forever. So I can say 0.7, but it's really not 0.7, right? Because I rounded it. But this is 0.7k equals r. Well, doesn't this look like y equals 0.7x? Doesn't that look like a linear relationship? Because k is just some constant, right? Some number that can change. Well, it's between 10 and 16. But this is linear, so this would be a linear relationship. Okay, the second part of this question is if we want to find the average global temperature increase in Fahrenheit if we are given a couple things here. One of the things is our T, our capital T here, is our global temperature increase, okay, in Fahrenheit. So that's our global temperature increase. And T of R is 1.03 R. Okay, so we're trying to get our T, which is our average global temperature increase. Okay, so that's our global temperature increase, and T of R is our global temperature increase in relationship to R. And so we want to write T. We want to write T as a function of K. Okay, so we're gonna basically this is kind of function inside a function. So that is 1.03 R, and R is equal to K of ln, K times ln of our C over C sub 0. So now I'm going to plug this in, right? I'm going to plug this in for R into here, okay? So T of R is our 1.03 times by our R, which is K ln of C over C sub 0. So then we can just multiply that in there, and we get T of R. So our average global temperature increase is 1.03 times our K, times our constant, times ln of C over C sub 0. And so now we could, given any we know our constant is between 10 and 16, and if we know what our current carbon dioxide level is in the relationship to its pre-industrial one, then we can go ahead and find out what our average global temperature increase is. Okay, so that's those examples for that. We'll go ahead and do these homework problems 75 and 77. Also real quick, because I replaced my R, this actually should be a K right here, right? Because that's my variable that I want to put in that constant, and that allows me, once I know what my current carbon dioxide level is in relation to the pre-industrial, then if I just have my constant, which is somewhere between 10 and 16 for this example, I can go ahead and figure out what that temperature increase is. So K, once I plugged in what R is, then this variable is now in relationship to K, right? Because I have no more R in there. Okay, so let's go ahead and do this example. So here we have that same formula. right? And we want to find the average global temperature increase, and we want to go ahead and, where is it? Okay, and they say when C is doubled, so when our current carbon dioxide levels double that of our initial pre-industrial carbon dioxide levels, what is our K? So we're going to solve for K here and figure out what our T of K would be, or find out what our K would be. So this is double, so it's 2 times, C is 2 times that of CO, 2 times that of CO, so these will cancel, we get 2, so we get ln of 2 times K times 0.03. So we actually want to find that temperature increase, and our K is between, just like the examples, between 10 and 16. So they don't actually give us a K here, but we know it's somewhere between 10 and 16, right? So if we just plug in 10 for our K, we can see what we get. So I'm going to take 1.03 times 10, which is just moving the decimal place over 1, and then times that by ln. Okay, so this is 10.3 times ln of 2. So I'm going to type that in the calculator. And that is 7. So, oops. T10 is approximately 7.1. See if it asks around. Nearest degree. So we're asked around to the nearest degree, so we'll say 7 degrees. Okay, that's when it's 10, right? Well, now let's figure out at its where K is at its max, 16. So now we're going to plug in 16. So 16 times 1.03 times ln of 2. Okay, and that will give us our T at our max. So then we know, okay, what is our lowest possible increase, and what's our highest possible increase. So we might not know exactly what the increase is, but we know the range of our increase, right? So we're going to type 1.03 times 16 times ln of 2 and we get 11.4, so it still says at 11. So our range is somewhere between 7 degrees Fahrenheit and 11 degrees Fahrenheit. So that's where somewhere our temperature increase is somewhere in between there. All right, now we can do number 77. We're looking at the age of rocks. So remember, the age of rocks formula is 1.26 times 10 to the 9th. This is our age of rocks. Can't remember the letter that they let it stand for. And then we times that by ln of 1 plus 3.88 times by A over K, and then we divide that by ln of 2, right? Okay, so they're going to let our A over K equal 0.103, and we want to go ahead and figure out, what is the age of this rock. Just let me make sure I get my, 8. This is wrong. This is 8.33. Okay, so then we're going to take 1.103, so 0.103, and I want to multiply that by 8.33, and I get 0.85799, which I'm not even going to write that down because I'm just going to keep that in my calculator. Okay, and now I'm going to add 1 to that. Okay, so I want to add 1 to that, so I'm just going to put plus 1 equals a number. Okay, 1.85, I'll write this one down, 1.85799, and then I want to take the ln of that. So I want to hit ln on my calculator, and then I want to hit the answer button, parentheses, and then I want to hit divided by ln of 2, and put that 2 in parentheses. and it equals, so I got my number, it's 0.894 something. And then I'm going to times, so now I'm going to hit multiplication, times by, and now I'm going to put this in parentheses. So parentheses 1.26 times 10 raised to the 9th, end my parenthesis. And then I get my answer as 1,126,115,849. So that is 1.1 billion. So 1.1 billion would be the answer there for number 77. That's how many years this rock, whatever it's estimating. Okay, so that's it for application problems. These are a little tougher, right, because you got to read through it. You got to use a formula. Where do you put it in? Especially that temperature one. I don't even like doing that one. So you kind of got to read through these, follow the examples the best you can. But here are these two problems.